So for our first example, let's look at an automated gate, also called a turnstile. So we all know this, we've seen these types of gates in any entrance. So the operation is that of this device is that it has three arms, and these three arms could rotate, and initially they are locked, and if you are suppose give a coin input, or if you are allowed to go in, then this circular arms will be unlocked and you could pass through this gate. And after you pass through, this turnstile will be again locked, and so no one can enter through this passway. Okay, so how do we go about design something like this? On the right hand side we can see what we call a state diagram. So basically what we're defining is that our circuit or our circuit will have two states. One will be it will be locked, and it will be unlocked. Whenever it is in locked state, it means no one can pass through. Whenever it is in locked state, if we input a coin, then our circuit will go to the unlocked state. So whenever it is in unlocked state, we can enter through this turnstile. And if it is when it is unlocked, if another person puts another coin in, then it will be unlocked until we have no coin. So whenever we have put in a coin, it will be unlocked, but if we go through, and it will be again locked. So when we push through the turnstile, so when we push through it, it will again be locked, and this will be our state. So we can see this push input as some sort of a sensor that senses whether we have, if anyone is pushing the door or not, or the arm or not. So then we have our state table. Okay, so the when we have our current state could be locked or it could be unlocked. When it is in locked state, if we input a coin, the next state will be unlocked. So unlocks the turnstile so that another customer can push through. But if we are in locked state here, if you are in locked state and we see a push, so someone is trying to go through our turnstile without putting in a coin. So what we do not let that person in. So our next state will be locked and nothing output. So it stays in this state, locked state, until we see another coin. Is this one. And whenever we are in the unlocked state, if we have an input coin, then it will be unlocked. It means that we will loop through this state. So if we keep putting in coins, we will let people in. And but whenever it is in unlocked state, if someone pushes through, so someone, after putting the coin, when it is unlocked, someone goes through the turnstile, it should again be locked, so not more than one person can go through using one coin. So the next, whenever we are in unlocked state, when someone pushes through the door or goes through the door, our next state will be locked, and when the customer has pushed through, it locks the turnstile, so no one can pass through using the same coin multiple times. Now another example we will be seeing is that the electronic combination lock. So here we have the diagram of our system. We have a reset button, an input for 0, an input for 1, and we have the unlock signal. So this is some sort of an electrical lock. And let's say we set the combination to be 0 1 0 1 1. So if we create this combination using these two buttons, so first we press 0, this one, and then we press 1, then we press 0, then again 1 1, and our if we put this combination, this lock should unlock, and it should generate a signal to unlock something we have previously locked. So this is another example of where we can use our finite state machines. So here is our state diagram for our combination lock. So our combination, if you recall, was 0 1 0 1 1. Of course, we should have a reset state. Every machine should have a reset state. So whenever we reset, let's say we go into this first state. Okay, so this is our first state. So if we press the button 0, the machine should remember that someone has pressed a 0. So we switch our state from this to this. So whenever we press a 0, we remember that one single 0 has been pressed, but we still shouldn't unlock the lock because our whole combination has not yet been put in. So our state will still be, our lock will be still locked. So when we are in this state, only one 0 has been pressed. If we press another one, so 0 1, we should remember that someone has put in a 0 1. So whenever another one is pressed, we should remember this and move on to the next state. So in this state, we say that someone has pressed 0 1, but it is still not the complete pattern for unlocking, so our unlock should still be 0. But if someone pressed 0 instead of 1, so we have first we press 0 and then someone pressed 0, so 0 and 0. I'm talking about this state. So if someone presses a 0, so this does not match any pattern in our original unlocking pattern. So we just keep looping onto this state. Okay, so someone should press 0, and then when we are in this state, okay, so someone has pressed 0 1, and then if someone presses 0, we should remember that. So now our combination is now 0 1 0, and we move on to the next state. And similarly, if someone presses another 1 after, we go to this state, so 0 1 0 1. And finally, when we are in this state, if someone presses another 1, we move to the next state, which is our 0 1 0 1 1 combination, which is our previous combination here. So as the pattern is matched, we should unlock our lock, electronic lock, and generate this signal, and this should unlock our original device. So as we can see that we have just gone through the pattern which unlocks our lock, but as we know that there could be many such configurations like 0 0 0 1 or any other combination but this. So those combinations are being drawn here, like first we talked about this one, and whenever we have 0 1, but if someone pressed 1, we should go back to our first reset state, and if someone pressed 0 1 0 and then 0, we should go to this state. So if we consider every scenario, then we should be able to build this kind of state diagram. And one thing to note about this state diagram is that each node, we say these states, we should call these states as nodes, and each node should have two outgoing transitions. So our input could be either 0 or 1. So depending on these two inputs, our each node should have two outgoing branches. So if if you consider this whole state diagram, we can see that each of the nodes should have two outgoing nodes, or we should call this transitions or edges. So if we can make sure that every node has two outgoing edges, then our ultimately our ultimately our state diagram will be completed. And another thing to note here is that for this particular combination we used about 6 states. Okay, so we have 6 states, and we know that to represent 6 states or six individual states in binary, we should need 3 bits. So that is another thing to note in this slide. And another example is the counter example, which means it's just basically a counter or a stopwatch. So what it does is just counting. So we have a 3-bit binary counter, so we have 3 bits on each state. So whenever there is a clock pulse, we up count. So first we have the 0, then we have 1, we have 2 and 3, and so on. We go on to up to 7, and then we again turn back and go to 0. So this is another example of an FSM where we could use these finite state machines to design any counter, which could either be up counter or down counter or any other types of counter that we might need to build. Another very prominent example of a FSM application is that the building of the control circuits of a processor. So on this slide we can see that we have a multi-cycle MIPS microarchitecture. So the details of this circuit and this processor, you don't have to memorize it. Just we are just demonstrating where the FSM could be used. So as every microprocessor, this is no different. We have a memory, we have the registers and other ALE units and other program controllers. So one of the most important parts of a microprocessor is that we need to have a control unit which controls or which generates the control signals needed to the ensure the correct operation of a microprocessor. So as we can see that we have a clock input to our control unit, and we have different control signals such as PC write, branch, PC source, ALU control, ALU source B, ALU source A, register write, OP, opcode function, and other memory write, IO write. These are some of the control signals that this control unit should produce with every clock input. So for this kind of application we could build such an FSM that does this job perfectly. So this is the example of the control unit of the MIPS cycle processor that we saw before. As we can see that this is our reset state, and depending on the different combinations of the inputs and outputs, we loop through the each of these state diagrams. So this is the complete state diagram of a control circuit of the multi-cycle MIPS processor.